And what we learned is that Smith chart is a graph like any other graph. The Cartesian coordinate graphs, Smith chart is also a graph. What is the difference between these two? In the Cartesian coordinate graph, you have a x-axis, we have y-axis, and the lines, the grid lines are parallel to x-axis and y-axis. Whereas in the Smith chart, we do not have a x-axis or y-axis. What we have is circles and arcs. Arcs are the parts of circles. Now, on these circles, complete circles are having their centers on the x-axis. Similarly, the arcs are having their centers on the y-axis. Since they are having their centers on the y-axis, if they are above y is equal to 0, so then those are positive arcs. Below y is equal to 0, those are negative arcs. Positive arcs represent the inductance. Negative arcs represent the capacitance. Resonance, inductive impedance or inductive reactance is equal to j omega L, which is positive. Capacitive reactance is equal to 1 by j omega C, which is equal to minus j omega by C, minus j by omega C, which is negative. Therefore, the upper portion in the Smith chart represents inductance, lower portion represents the capacitance, and the horizontal line that represents the pure resistance. There is no inductance or capacitance involved. Now, today what we will do is, we will try to see some examples, and I will like if you can work out these examples yourself. We are going to give you some problems, simple problem we will give, and we will see how to solve those problems so that you will be able to understand how to use this method. So let us start with one example, a simple example. We have a transmission line which is terminated on a load ZL. ZL is equal to 100 plus J50 ohm. So 100 is the resistive part, 50 is the reactive part. Since it is plus J50, it is inductive in nature. So reactive part is inductive. So ZL is equal to 100 plus J50 ohm. Characteristic impedance of the transmission line is 50 ohm. We have to find out what is the input impedance at a distance d from the load when d is equal to or d by lambda g. Lambda g is the wavelength, guided wavelength. Lambda g stands for guided wavelength on the transmission line. So when we are at a distance of d by lambda g, which is equal to 1 by 4 or 3 by 8 or 1 by 2. At these three distances from the load towards the source, as we move from load towards the source, if you move a distance of lambda g by 4, then what will be the impedance, input impedance seen at that point? If we move a distance of 3 lambda g by 8, what will be the impedance at that point? And if we move a distance of 1 by 2 lambda g, what will be the impedance at that point? Since we are interested in impedance, we use the impedance chart or the J chart or the Smith chart. Now, as we have discussed earlier, the Smith chart represents normalized impedances. Normalized impedance means find out what is the impedance, and then divide the impedance by the characteristics impedance of the transmission line or the waveguiding structure. So here the characteristics impedance is 50 ohm. Impedance of the load is 100 plus J 50 ohm. Therefore, normalized impedance ZLN. First thing is find out what is ZLN. ZLN is equal to ZL by Z0. Normalize the impedance with respect to the characteristics impedance. So ZL by Z0, that will be 100 plus J50 ohm by 50, that is equal to 2 plus J1. Now this point we have to plot on this Smith chart. How do we plot this point on this Smith chart? That is the question. So first, I'll look at what is the resistance value. ZLN is equal to 2 plus J1. The resistance, normalized resistance, is equal to 2. So look for the complete circle which corresponds to Rn is equal to 2. So you can see that there is a larger circle which represents the outer circle of the Smith chart. There is an inner circle, the black inner circle. Look at the black inner circle, that is the inner circle on the Smith chart. That is for Rn is equal to 1. Then there will be a smaller circle. Similarly, as you keep on increasing Rn, so there will be a smaller circle. You can find out if you have the Smith chart. Find out the smaller circle for which Rn is equal to 2. So first locate that smaller circle. Rn is equal to 2 circle, locate that. Then we have J1, which is positive. So look at the upper part of the Smith chart. Then look for Xn is equal to 1. Xn is equal to 1 will be the middle one, the middle arc. All the arcs, out of all the arcs, the mid arc is Xn is equal to 1. So along that arc, everywhere, every point on that arc, Xn is equal to 1. So move on that arc from the periphery towards the Rn is equal to 2 circle. Wherever that arc meets the Rn is equal to 2 circle, or wherever that arc crosses the Rn is equal to 2 circle, and locate that point and mark that point. Here on this figure, the figure that we have shown in the figure, look at the upper red dot. The upper red dot is ZLN. That is the point where Xn is equal to 1 and Rn is equal to 2. So through that point, if you draw the circle, if you look at the resistive circle, for that resistive circle Rn is equal to 2. And if you look at the arc passing through that circle, for that arc Xn is equal to 1. So that is our ZLN, normalized impedance point on this Smith chart. So first locate the normalized impedance point. That is first point. Second point is, second thing that you have to do is, once you know what is the normalized impedance point, go to take your rounder and put this one side of the rounder on at the center of the Smith chart and draw a circle which passes through this ZLN, which passes through the normalized impedance point. Draw that circle. If you draw that circle is called constant VSWR circle. As you know, on the transmission line, VSWR always remains constant. Although gamma will remain constant, VSWR will remain constant. What will change is the value of the impedance. As you move along a transmission line, value of impedance changes, but the amplitude or magnitude of gamma or reflection coefficient is fixed, and magnitude of VSWR is fixed. So on that will be fixed. So this circle is called the constant VSWR circle. First draw this circle, constant VSWR circle. Then from the transmission line theory, we know if we move a distance of lambda g by 2 or half wavelength along a transmission line, then the impedance is repeated. Suppose at any point on the transmission line, the impedance is Z, then if you move a distance of lambda by 2 from that point towards the source, then again the impedance will be Z. If you move a distance of lambda G by 4 or quarter wavelength from that point, then the impedance will be inverted. So if it is Z, then after a distance of lambda G by 4, it will be 1 by Z. So after every quarter wavelength, it is inverted. After a complete wavelength, the impedance is repeated. These are two important conclusions that we have seen from the transmission line theory, in which we have seen what is the expression for input impedance. Zin is equal to Z0, ZL plus J Z0 tan beta L divided by and Z0 plus J ZL tan beta L. From that equation, we can always infer these two conclusions. Now we have found out this point Ln, normalized Z point. And the first question is, what will the impedance after 1 by 4? After d by lambda g is equal to 1 by 4 or d is equal to lambda g by 4. Now how do you find out d is equal to lambda g by 4? What is that distance? That you can find out easily by moving half a circle on the VSWR circle. So what you will do is draw a line, straight line, passing through the center of the Smith chart and ZLN. So draw a straight line. So that straight line, elongate the straight line. So that straight line, you can see there is a straight line which is passing through ZLN and the center of the Smith chart. So that you have to do. And then on the VSWR circle, move half a circle. Why we move half a circle? The reason is very simple. Look at ZLN. If you move one complete circle, then you have started at ZLN and came back to ZLN. Now, if you start at ZLN, come back to ZLN, that requires lambda g by 2 distance to cover. So one complete circle is lambda g by 2 distance. So half a circle is equal to lambda g by 4 distance. So if you are moving lambda g by 4 distance, move half a circle. So if you move half a circle, so you will come to the point A that is shown on the figure. This next red dot line, which is on the lower half, you will come to that point. You will be reaching at that point. So that will be the point A, the red dot. Now, once you reach there, I'll read what are the values for A. So find out the arc which is passing through the point A. That arc will correspond to minus 0,2. Then find out the circle which is passing through that red dot at A. That will be approximately 0.4. So Z at A will be the impedance at A. A is the point for where we have traveled lambda g by 4. As I have now explained, A is the point for which we have traveled lambda g by 4 from the load towards the generator. As I discussed in the last class, if we are moving towards the generator, it is a clockwise rotation. If we are moving towards the load, it is an anti-clockwise direction. So move in the clockwise direction from ZD half a circle, reach the point A, locate and find out what are the coordinates of A. R coordinate is 0.4 and X coordinate is minus 0.2. So Z in and Z is equal to 0.4 minus J 0.2. Remember, this is the normalized impedance. If this is the normalized impedance, what is the impedance? Impedance will be normalized impedance into Z0. So multiply Z0 in ZA. So if you multiply Z0 in ZA, that will give you Z is equal to 0.4 minus J 0.2 whole into 50. 0.4 into 50 is 20. J 0.2 into 50 is 10. So the impedance will be 20 minus J 10. So that is at a distance of lambda g by 4, the impedance now will become 20 minus J 10. So using a graphical method or a graphical tool, which is the Smith chart, we can easily find out the impedance at a distance of lambda g by 4. This is example. This is a simple example that we have seen. Next, let us see lambda d is equal to 3 by 8 lambda g. So that will be so we have to find out d is equal to 3 by 8 lambda g. At that point, what will the impedance? So start again from the normalized impedance. Rotate by a distance, move on the VSWR circle a distance of 3 by 8 lambda g. That is the point B that you can see the blue dot. That shows you 3 by 8 lambda g. We have rotated or moved along the VSWR circle by a distance of 3 by 8 lambda g from the normalized distance point. Now find out what are the impedances of point B. So how do you find out the impedances of point B? Find out the circle that is passing through the point B, that will give you the R, and find out the R that is passing through point B, that will give you X. So using that, we will find out normalized Z will be approximately equal to 0.5 plus J 0.5. Then find out what is Z. Multiply 50 with normalized Z. So that will be 25 plus J 25. So if you move a distance of 3 by 8 lambda g, you will reach at that point. Okay. Now, I remember this thing. 3 by 8 lambda g, when you move 3 by 8 lambda g, I have told you earlier that the Smith chart gives you a complete circle along the perimeter of the Smith chart, or on this Smith chart, if you move one complete circle, that is equivalent to 0.5 lambda g. So you start at 0.0 lambda g or 0 lambda g and move a complete circle, you have come to 0.5 lambda g. Then it is reset. Again, it will start from 0.0 lambda g. You will come back to 0.5 lambda g. Again, it gets reset. Then again, you go from 0.0 lambda g to 0.5 lambda g by completing one cycle or one circle. Now, when we are at ZLN, ZLN is equal to 3 by 8 lambda g. Sorry, ZLN has some value which is more than 0 lambda g. It is not 0, it has a positive value. Now, if you move 3 by 8 on from ZLN, then there is a problem. The problem is it can be more than 0.5 lambda g. So whatever is the value of lambda g there, whatever distance you have covered from the short circuit point in moving to ZLN, that distance plus the value of ZLN. So that must be accounted for. To account for that, what we do is we find out what is the distance that you have covered up to the point ZLN, that is 0.212 lambda g. 0.212 lambda g is from 0. Look at the Smith chart perimeter towards the generator. Towards the generator, if you look at it, you will see 0, 1, 2, 0 lambda g to 1 lambda g. 0 lambda g, 0.1 lambda g, 0.2 lambda g. So that way you will see 0.001 lambda g. All those you will see on the perimeter as we have seen in the last class. So outer circle, look at the outer circle where it is written towards the generator, and there the wavelength is given. So follow that wavelength up to ZLN in the clockwise direction. So you will see that that distance is that on length of the wavelength that you have traveled from the open circuit, short circuit end is this much, 0.212 lambda g. So you start at 0.212 lambda g. From 0.212 lambda g we add 3 by 8 lambda g, because we have to move 3 by 8 lambda g. That is in the question, we have to move 3 by 8 lambda g. Now when you add 3 by 8 to 0.212, that will be more than 0.5. It gets reset at 0.5. So what we will do is add these two, then reset it. For resetting, subtract 0.5. So 3 by 8 plus 0.212 minus 0.5. That will be equal to 0.087. So to locate B, the point B, how do you locate point B? Locate for point B by moving 0.087 lambda g from the short circuit end towards the generator, move from the short circuit point, or lambda g is equal to 0 point, move a distance of 0.087 lambda g, and join that distance, that point to the center. So that will cross the VSWR circle at the point B. So then you can find out what are the values of B, what are the values of resistance and reactance at the point B. So this is how you will find out D is equal to 3 by 8 lambda g. Then the last one is very simple, lambda g by 2. As I told you, it repeats every lambda g by 2, so there is no point. You start at ZLN, make one complete circle, so you are reaching at ZLN, so there will be no change in the impedance. After one lambda g by 2, it will be 100 plus J50. So this is one example. We will see the second example. Another example, this is using the Smith chart or Z chart. Let us use the Y chart. Same process, let us use the Y chart. Here what is given to us is Z0 is equal to 50 ohm. We have got a transmission line. Z0 characteristics impedance of the transmission line is 50 ohm. Therefore, characteristics admittance of the transmission line will be 1 by 50, which is equal to 20 millisieverts. Answer 20 ms or 20 millimoles, whatever you can say. Similarly, YL or the admittance is given 8 ms minus J4 ms. Now what we have to do, repeat the same thing, find out Y at D is equal to lambda g by 4, at D is equal to 3 by 8 lambda g, and at D is equal to 1 by 2 lambda g. So since it is the admittance, we will use the admittance chart. In the admittance chart, the difference between admittance chart and impedance chart is, in the admittance chart, the upper part becomes negative, lower part becomes positive. So upper part gives you negative susceptance, lower part gives you positive susceptance. That is the difference. Otherwise, it is basically a mirror reflection of the impedance chart. So first thing is you normalize the admittance. Given admittance is to be normalized. So YLN is equal to YL by Y0. So find out what is YL by Y0. That will be 0.4 minus J0. Then first is question number 1 is D is equal to 1 by 4 lambda g. So D is equal to lambda g by 4. First locate where is YL. So 0.4 circle. You will find out what is the 0.4 circle. Then you will find out what is the minus J0.2 circle. So those two circles you will find out. From their intersection point, find out their intersection point, which is the point A. Then you rotate it, draw this a constant VSWR circle, which is the blue circle. Once you draw the circle, then you have to move a distance of G by 4. Now G by 4 means half a circle. So half circle move from there, on that move half circle. So if you move half circle, you will reach at the point A. So once you reach at the point A, that is your answer. So A will be YA is equal to 2 plus J1. Then to get the exact value, multiply that with Y0. So if you multiply that with Y0, it will be 40 ms plus J at 20 ms. So that is capacity. Then for point B, follow the same principle as in the previous case. You will find out on the point B. Point B will be on the upper part of the Smith chart in this case. Then point C, it will be repeated. You start with YLN, go by lambda by 2 distance, it will be repeated, so there is no problem there. There will be no change. Whatever was YLN, we will get that back. So that is, these are two simple examples. I will give you 5 minutes in this time. Maybe you can do this. If you cannot do it, you can ask me if you have a doubt in doing this hands-on on a Smith chart. You can ask me, I will guide you. Otherwise, we will see additional examples. After 5 minutes, we will see some more additional examples, so that it will be easier for you to draw these Smith charts. So let us take a break of 5 minutes. In this period, you please try to do this. You can use these examples that I gave you, or you can have your own examples also.